Welcome to a series of lectures called Glass, Selected Fundamentals, Basic Principles and Background Information. My name is Christian Roos. I'm professor at RWTH Aachen University and head of the chair of Glass and Glass Ceramic. This video series is intended to give background information on selected aspects of glass science and to reinforce the content of the lectures. The videos are not based on the structure and thematic sequence of the lectures, however. Today's video is about the fragility of glasses and the so-called Angell plot. Now, from a structural point of view, there are basically two so-called frustration mechanisms with which a melt can reach an uncrystalline state. The first one is frustration due to large polymer units, meaning the network is highly connected and is not able to rechange to a crystalline structure. The second mechanism that can avoid crystallization is the incapability of space filling via sphere packing, which means spheres, like as we consider atoms as spheres, can, due to its coordination structure, not be packed in a space-filling way, for instance like in a cubic closed packing. We've learned that the glass melt has at the glass transition a viscosity of 10 to the power of 12 Pascal seconds. Also, it can be concluded from various investigations that there is something called a high temperature limit of viscosity. And this limit is at approximately 10 to the power of -5 Pascal seconds. The behavior between these two viscosity limits, so between the high temperature viscosity and the transition viscosity, depends on the degree of polymerization of the melt and on the aforementioned structure or the frustration mechanism. Let's have a look at the heat capacity curve. When the melt crystallizes, the heat capacity changes instantly to the heat capacity of the respective crystal. When the melt is undercooled and a glass is formed, the heat capacity changes gradually to the heat capacity of the respective glass. The difference between the heat capacity of the melt and the glass is a so-called CP jump, delta CP, which is used in many calculations. The height of this CP jump depends on the polymerization of the melt. If the melt is already fully polymerized, the CP jump of such a melt basically disappears. Now, if one plots the viscosity of a glass in the range of the high temperature viscosity and the low temperature viscosity in the glass transition as a function of a universal dimensionless temperature, one achieves a so-called Angell plot. In the Angell plot, the temperature is plotted as Tg divided by T, meaning at the value of 1, Tg equals T. So we have Tg divided by Tg. This gives us 1. And in the high temperature range, we approach 0 because the higher T gets, the lower the value Tg divided by T gets. Now, the viscosity curves of different classes in this range show different behavior according to their mechanism of frustration that was mentioned earlier. And the most characteristic point is the slope with which Tg divided by T equals 1 is reached. So the slope with which the viscosity curve here reaches the value 1 in the Angell plot. If we consider a fully polymerized melt, for instance a pure SiO2 melt with a Q4 structure, as mentioned earlier, the CP jump from the melt to the glass becomes neglectable. Such glasses are called strong glasses, as you can see here by this curve. In addition to that, the slope with which these strong classes reach the value of Tg divided by T equals 1 is small. On the other hand, glasses with mainly ionic bonds or less polymerized glasses have a quite large CP jump when changing from the melt structure to the glass structure. Such classes are called fragile classes, and the slope with which they reach the value of Tg divided by T equals 1 is rather large. This can be seen here. So by looking at the viscosity behavior of different classes in the Angell plot, one can deduct if it's a strong class, which is highly polymerized, or if it's a fragile class, which has a low polymerization. Hence, the measurement of the viscosity gives us information about the structure that can be observed in a class. So the Angell plot gives us a possibility to determine the structure of the class with viscosity measurements. As mentioned in the previous slide, for strong classes, fully polymerized, for instance Q4 structure, there is a high reluctance in restructuring and they are easy class formers. And because no decrease of freedom, meaning configurational or rotational entropy, can be lost, as the structure is already fully polymerized, the CP jump from melt to class is very small. On the other hand, for fragile classes, their frustration mechanism is due to the incapability of packing the structural units in a closed space-filling packing. And because in that case, the class or the melt still has the configurational and the rotational entropy that is lost from the transition melt to class, the CP jump of these classes is quite large. The respective slope in the Angell plot, which is helpful to determine the polymerization degree or the frustration mechanism, can be calculated from the respective temperature-viscosity equation. This can be, for instance, Vogel-Fulcher-Tammann or Adam-Gibbs equation. If we apply Vogel-Fulcher-Tammann to the Angell plot, we have this relation here for the slope, or if we apply Adam-Gibbs, we get this expression here for the slope in the Angell plot. And again, with these slopes, one can determine the respective structure, polymerization degree, and frustration mechanism of the respective class. With this, we are at the end of this video, and I trust it was helpful for your further understanding of class science.